My name is James Johnston, and my integrated project study was looking at the effect of hydrolysed polyacrylamide polymer contaminated petroleum-produced water on a surface flow constructed wetland in Oman. Firstly, I would like to give you an overview of what I've been involved in for the last 6 months. I've been doing my internship and integrated project for a company called Polymer in the Sultanate of Oman in the Middle East. Polymer treats 95,000 cubic meters per day of produced water that is a byproduct of the extraction of crude oil. The Nimmer water treatment plant uses a series of surface flow constructed wetlands to remove the hydrocarbons and disposes of the water into the atmosphere through the use of large evaporation ponds. The whole system is gravity fed, which reduces energy consumption by up to 98% when compared to deep well disposal, which was used before the project started operation in 2010. This slide shows a layout of the plant. The top photograph shows a panoramic view of the wetlands, and the bottom two aerial pictures show the plant layout. It should be noted that the aerial photograph on the bottom right is from 2011, and by comparing it to the aerial diagram on the bottom left, you can see that the project has nearly doubled in size. Produced water enters the system via a pipeline before going through an oil and water separator pictured here. The produced water is passed through the Stilling Basin and series of cyclonic oil separators where a majority of the oil is removed. The water is then channeled down a buffer pond for distribution into the wetland through 9 parallel surface flow wetland tracts. Each of these tracts consisting of 4 terraces. The average hydraulic residence time of the wetland is 4 to 5 days. Once the water has been treated by the wetlands, it finally enters the reservoir, evaporation ponds, and saltworks facility used for salt recovery. From this diagram on the top right, you can see that primary methods of oil extraction, such as natural lift and pumping, extract about 30% of in-place oil, and secondary methods, such as water flooding, remove between 30 and 50% of this oil. After these methods have exhausted all available oil, tertiary extraction or enhanced oil recovery techniques are used. Polymer flooding is one of these techniques. This diagram on the bottom of the slide depicts how polymer flooding is done. Solid polymer granules are diluted in water at the surface and then pumped into the reservoir via an injecting well. This polymer thickened solution has a higher viscosity than water, so is more effective at sweeping or pushing the oil to the producing well. The result is improved volumetric sweep efficiency. That is, more oil is produced for a given volume of water injected into the well. Post-2016, the Nimmer oil fields will start using polymer-assisted enhanced oil recovery using hydrolysed polyacrylamide, what is commonly known in the industry as HPAM. For this reason, Bauer Nimmer needs to know what effect the polymer-contaminated water will have on the wetland treatment plant. This slide shows a brief overview of the aims and objectives of the study. The study will be split up into 2 parts. The use of wetland mesocosms to study the effects of the HPAM polymer on the wetland plant growth, health, evapotranspiration, evaporation, and the degradation of the HPAM polymer in the wetland system. The second part of the experiment will use column infiltration experiments to study the effect of the polymer on the infiltration rate of the mineral sealing layer used in the wetland. So firstly, we'll look at the mesocosm experiments. It should be noted that Bauer intern and SCU student Mitchell Kirby set up and initially monitored the mesocosm experiment during the August-October 2012 period. All other monitoring was done by me. Each treatment was done in triplicate for more scientifically valid results. It consisted of a combination of 7 treatment variables, which varied according to HPAM polymer concentration, 0, 200, or 500 parts per million, planting status, planted or unplanted, and salinity, 6 or 12 parts per thousand total dissolved solids. The layout of the mesocosm experiment is shown in the bottom photograph. 27 mesocosms were constructed from intermediate bulk containers or IBCs pitched in the top right corner. These were then filled bottom to top with 10 cm of coarse gravel for good drainage, 20 cm of soil substrate, as used in the main wetlands, a water column depth of 10 cm, and then a freeboard of 10 cm. The planted mesocosms were then planted with 20 Phragmites australis seedlings, the dominant plant species in the main wetland. The operation of the mesocosms was done differently depending on which treatment. The effect of a constant polymer concentration was done on a weekly batch load system. This meant at the end of each week the mesocolumns were drained and then filled up with their respective polymer concentration. 20 milliliters of Nima crude oil was also added. The mesocosms that were used to study the effect of a single dose of polymer on plant health was run on a single 8-week treatment. That meant at the start of the study, a single respective polymer concentrated solution was added to the mesocosm and a single 20 milliliter dose of Nima crude oil. Every 2 days, the water loss from each mesocosm was measured from a marked datum and topped back up with water. The sampling parameters of the mesocosms are as follows: water loss due to evaporation and evapotranspiration, plant health and growth. This was done by putting 5 randomly placed quadrates into each planted mesocosm and measuring. Shoot height, done by measuring all shoots in each quadrant. Shoot density, by counting the amount of shoots in each quadrant. Above ground dry biomass, involved using a correlation curve for shoot height and weight outlined in this graph. By using this equation of the line highlighted in red, as well as the shoot height and shoot density measurements, an estimated above ground dry weight could be calculated for each mesocosm. The actual harvested above ground dry weight was also measured at the end of the study. Another plant health parameter was leaf health, and was measured on the young newly formed leaves and the aging older leaves. This was done by simply measuring the percentage of green, live leaf to brown, dead leaf. This browning of leaves is termed necrosis, and the complete death of a leaf is termed chlorosis. Leaf nutrients and trace elements were also analysed by an external laboratory at the end of the study for elements such as nitrogen, phosphorus, and boron, etc. Physical water parameters were also measured regularly, as well as sending samples to an external laboratory to analyse viscosity and acrylamide concentration. The measurement of viscosity is one way to indirectly measure the amount of polymer in a solution, and the acrylamide concentration relates to the potentially toxic breakdown product of the HPAM polymer. Here are the results of the above ground dry biomass, top graph, and the shoot density, bottom graph. In both parameters, the read showed an even steady increase up to week 5. This was due to the plants getting established in the mesocosms. After week 5, the polymer-treated plants increased growth at a much higher rate than the treatments with no polymer. Although the average measurements across the mesocosms show this trend, there was a large variation between replicates, meaning that when a one-way ANOVA test was done, it showed no significant difference between the treatments. This increased growth in some of the polymer treatments was most likely due to the increased nitrogen from the HPAM polymer addition. If we have a look at the HPAM polymer chemical structure, we can see that it has nitrogen in the form of NH2. It is believed that the increased growth was due to the plants utilising this nitrogen as a fertiliser in an otherwise nitrogen-lacking environment. This slide shows the results of the necrosis and chlorosis of the leaves. The top graph shows the percentage amount of dead leaf on the young, newly developed leaves, and the bottom graph shows it for the aging older leaves. In terms of the young leaves, the polymer treatment showed higher necrosis than the no polymer treatment, staying relatively steady over the study period. In terms of the aging leaves, there was a steady increase in necrosis in all treatments, although the polymer treatment showed much higher rates, as high as 85% of aging leaf necrosis over the 6-week period in the 500 ppm polymer treatment. Some answers as to why this necrosis and eventual chlorosis occurred can be found in the leaf nutrient and trace element results from the external laboratory. All of the polymer-treated plants showed an increase in potentially toxic chemicals such as boron, manganese, copper, molybdenum, nickel, and zinc. This can be seen by comparing the values of the no polymer treatment, highlighted in red, to the polymer-treated plants, highlighted in blue. The leaf necrosis and chlorosis was most likely due to boron and/or manganese toxicity, as browning and yellowing of the leaves is a common symptom. Why the polymer-treated plants had an increased uptake of these potentially toxic chemicals is unknown and requires further study. The nitrogen content of the leaves in the polymer-treated plants also showed an increase when compared to the no polymer treatment. This confirms the hypothesis that the polymer was a source of nitrogen for the plants. In terms of the evapotranspiration and evaporation from the mesocosms, up to the 6th week, the general trend followed the on-site Class A pan. After this time, the polymer-treated planted mesocosms showed a much higher water loss from the no polymer treatments. This was due to these plants having increased biomass and therefore transpiring at a higher rate. By looking at the evaporation rates of the non-planted mesocosms, highlighted in red in the table, it can be said that the polymer had no effect on the evaporation capacity of the water. This slide shows the results of the external lab measurements of viscosity, top graph, and acrylamide concentration, bottom graph, on day 0 and after 6 days of operation. The viscosity of the solution decreased over the 6-day period, suggesting that there was some degradation of the polymer. The acrylamide concentration also decreased over the 6-day period. This is an encouraging result given that there was some apparent degradation of the polymer in the mesocosms, but it did not result in the accumulation of the potentially toxic acrylamide monomer, a known neurotoxin, which is one of the potential breakdown products. Due to the large variation between mesocosms, in terms of above-ground dry biomass and evapotranspiration and evaporation, there was no significant difference between the treatments using a one-way ANOVA test. This was due to the small-scale nature of the experiments. The observed increased growth in some of the plants was most likely due to the increased presence of nitrogen from the HPAM polymer. It was found that the polymer addition had no effect on the evaporation capacity of the water. The increased leaf necrosis and eventual chlorosis observed in the polymer-treated plants was likely due to the increased uptake of chemicals such as boron and manganese. It was also found that there was some degradation of the polymer, and this degradation did not lead to an increase in the potentially toxic acrylamide. The second part of my study with polymers was looking at what effect the addition of polymers had on the infiltration rate of the mineral sealing layer. This was done using a full in-head permeability test, or FHPT. The experiment consisted of 12 PVC columns filled with compacted soil. The compacted soil was the same compacted material that is used to seal the main wetland. The test was undertaken in triplicate using 4 different polymer concentrations: 0, 200, 500, and 1000 ppm. The full in-head permeability test operation was as follows. After compaction of the soil, a 5-day initial infiltration test was undertaken with clean well water to get a base infiltration rate. After this, the columns were filled with their respective polymer solutions and monitored for 6 weeks. After these 6 weeks, a final infiltration test was done using clean well water. Every morning of the study period, the amount of water loss was measured and the columns refilled with their respective treatments to maintain a 20 cm head. The results of the full in-head permeability test showed that there was a rapid decrease in infiltration once the polymer was added in all polymer treatments. That is, the purple, red, and green line in the graph. The blue line, which was the no polymer treatment, showed a 20% decrease in infiltration over the study period. This rapid decrease in infiltration of the polymer-treated columns was likely due to the polymer blocking up pores in the substrate, as well as the polymer solution having a higher viscosity than water and therefore moving slower down through the substrate. Problems encountered during the experiment included not having equal initial infiltration rates. This was due to the method of compacting the soil not giving uniform compaction between the columns. Another issue was that there was a decrease in the clean water control infiltration rate, likely due to cracks opening up between the substrate and the PVC column due to heating and cooling by the sun. The results from both of these experiments, the mesocosms and the full in-head permeability test, are very encouraging for the NIMA water treatment plant, but there was also problems and issues encountered that need to be verified in future larger scale, longer term, more detailed experiments. Here is my recommended design proposal for the next stage of the study. It consists of 6 40 square metre surface flow constructed wetlands. Each basin will be split into 2, with one side fed with produced water containing polymer at 500 ppm concentration, while the other side receives produced water without the polymer. A dosing system will be used to supply the polymer to the inflow stream via a mixing tank. The system will look at the effect of polymer on a range of plant species including Phlegmites, Schunoplectus, Typha, and Juncus species. The effect of the polymer on the infiltration rate will also be studied further using a HDPE sealed wetland and comparing water loss to a wetland with a compacted mineral sealing layer. Thank you. Any questions?